welcome again to the Everything I Forgot from Stats class. I don't know what volume this is. I tried counting it up, and we've skipped some weeks and we've moved some things around. So I think this is like maybe 13 or 14, but I'm not 100% sure. Anyway, for this one, I kind of wanted to round out the conversation that I've been having with you all for the past couple of times I've been leading it on conditional process modeling. Because there's really two sides of the conditional process coin. Last time we talked about actually the last two times we talked about moderation. This time we're going to talk about mediation, and I'll talk just briefly at the end. We can talk about things like moderated mediation and mediated moderation. It gets real crazy with some of that stuff, but it's a really powerful stats tool, and you'll see mediation is becoming much more common. So just as a reminder, because moderation and mediation are so easy to mix up, I think I was probably a second-year grad student when I finally realized I had been saying them backwards for about 3 years. And that was quite embarrassing. And I don't want you to make the same mistakes I made. So moderation, which is what we talked about last time and the time before that when I was leading, this is simply an interaction. You're looking for an interaction between your two IVs, and they're going to come together and influence change in your dependent variable. Your independent variables do not need to be related by any means to be able to influence one another in this play. So moderation is simply it's like an ANOVA. It's like an ANOVA with continuous variables. You've got two things coming together to make multiple conditions that your dependent variable may be different at different levels of that moderator or different levels of that IV. So this was one of the examples I gave. You can see here, this is what a typical moderation output is going to look like. You're going to see you've got two conditions here on the right-hand side. You've got male and female. So those are categorical conditions. On the other hand, down here, we have continuous conditions. We have low social support that ranges from 1 all the way up to high social support, which ranges to 7. So people can fall anywhere along this continuum, and it would be inappropriate to categorize them because this is a continuous variable. And so when we interact these things together, we get slope. So we can see as social support goes down, so they go to low social support, depression scores increase. You can find a line through here. You can see scores on this line, and that's going to show you based on what social support and sex someone is going to predict depression scores based on this regression line. And you can see the lines and the slopes are different based on the group that individuals are in, but also the individual points are different based on whether they have high social support or low social support. You can see they get much further away at low social support with actually not a lot happening at high levels of social support. So that's just moderation. I emphasize that for a reason, because I want you to recognize that was moderation. We are going to be talking about mediation, which is different, but incredibly similar and so easy to confuse. So on the one hand, both of them, they involve three variables. They involve an independent variable, they involve a moderator or a mediator, and a dependent variable. Now, we can get real crazy with this and throw in tons of moderators and tons of mediation. And we can get into serial mediation or multi-level moderation. And we can keep going, but at minimum, they involve three variables and can only go up from there. You cannot possibly have moderation or mediation with only two variables or with only one variable. And similarly, the goal for both mediation and moderation is to determine how a third variable affects the simple relationship between variables. So with moderation, how does this variable impact this relationship? And for analysis-wise, they can both be analyzed with simple linear regression or multiple regression, technically, or structural equation modeling. So you've got Amos, you've got M+, several different softwares you can use to analyze this, or you can just analyze it in SPSS, as I'm going to show you how to do it in a moment. Now, one thing to remember, anytime I teach these, I teach them as a practical guide to, you should be able to take what I'm talking about and do it in whatever stats package you want. So I'm going to be using multiple regression to do all of this. So I'm not as fluent in like SAS, for instance, but when I talk about regression, you should be able to take these concepts and just do the regression in SAS the way you've been trained to do it there. So don't, Obviously, if you use SPSS, probably pay attention to the way I'm doing things. But if you don't use SPSS, don't fret. All you have to do is follow these sort of step-by-step goals and these step-by-step outcomes, and you can do this mediation in whatever stats package you want. So for differences between the two of them, in moderation, this involves product terms. If you remember when we computed a moderation, we multiplied our independent variable and our moderator together and got that cross product, just like you do in an analysis of variance. You don't do this with mediation. The mediator and the independent variable do not interact with each other. They are related, but they do not interact. If you remember, I taught you a strategy known as centering, where you subtract the mean from your moderator, or excuse me, where you subtract the mean from your dependent variable, and you don't have to do that here. It's typically required in moderation, but not in mediation. Now, you can if you want to. Centering is not going to change anything. It's going to change the scale things are on, but the overall regression formula is not going to change. The slope's not going to change. Your y-intercept's just only going to change because you've changed where it is crossing the line, but nothing's going to change. You can center if you want to. It'll probably run a little bit faster if you center it, but you don't have to. And if you remember, one of the things that I pointed out was if you're going to do moderation, you have to graph. You have to graph it. You have to understand the nature of that interaction, and you have to look for your simple slopes on that line. You don't have to in mediation, but I highly recommend graphing your mediation anyway. You'll see I've got some mediation graphs on here, and you'll see it makes it so much easier to try to understand the nature of the relationship. And also, if you're going to try and publish it, you need to show these. You need to show that graph. It's just so much easier to understand than just throwing numbers at somebody. Okay, so mediation. It refers to a situation when the relationship between a predictor variable and outcome variable can be explained by their relationship to a third variable, or the mediator. Many of you are thinking at this point, wow, that sounds very similar to moderation. And you're right, it's incredibly similar. The key here, though, is explained by their relationship to a third variable, not their interaction with a third variable. So in mediation, you have to have a relationship between your independent variable or your predictor and your mediator. Similarly, you have to have a relationship between your mediator and your outcome variable or your dependent variable. You don't have to have all of that in moderation. You only have to have that interaction, and then that interaction needs to be predictive of your dependent variable. That's it for moderation. So if we break this down into smaller parts, this right here is just a simple linear regression, a simple relationship. Your dependent variable or your independent variable or your predictor predicts your outcome variable or your dependent variable. Simple linear regression. You have run thousands of these in your career. I promise you of that. Nothing special. This is a mediated relationship. So if you see down here, we still have our simple relationship. However, we have another path happening here. This is what's known as your indirect path or your indirect effect, where your predictor predicts your mediator and then goes on further to predict your outcome variable through the mediator. And so the important question is whether a third variable or the mediator partially or completely controls the relationship between a predictor and an outcome. Oftentimes, when you have mediation, and as a matter of fact, there is a school of thought that says this is the only true time you have mediation. When you throw that, you may have a relationship here, but when you throw that mediator in, this relationship goes completely away. That's how powerful the mediator can be sometimes, because the predictor is affecting the outcome only through this mediator and doesn't do anything directly. So we'll talk about that a little bit more in a moment. But this is mediation, where your predictor goes through something else to predict an outcome variable. When I was learning this, my stats instructor liked to say, think of your mediator as a tunnel. This is one side of the mountain. This is the other side of the mountain. If you want to get from one side of the mountain to the other, you have to go through the tunnel. Yeah, you can go over the mountain, but that's more complicated. And we can talk about serial mediation and complex mediation later. But think of this mediator as the tunnel to get from point A to point B. And so I did I did a little bit of a search through some of the databases, and I wanted to look at just the number of mentions of mediation, mediator, or mediates. And I said medical journal, that was a typo. It's just health science or medical, so all that's included in there. Journal articles for between 1970 and 2010. I wanted to go up to 2020. It wasn't changing a lot of pictures though, so I just kept it here. Look at the drastic increase in the number of mentions of mediation. More and more people are doing mediation. And the reason for that, we're realizing that there can be some complex diseases or some complex conditions that are being impacted by other variables. And there may be things that are affecting these outcomes that we weren't expecting initially, that are going through other things or through mediators. So this is the way of the future. If you want to continue doing medical science, I strongly encourage you to be up to date on mediation, because you can see this is almost exponential growth if it keeps following this trend. So it's just increasing drastically. So let's talk about what mediation is and how to do it. The initial reference to mediation is from Barron and Kenny. I put the joke up there, I wish I was cited like that, because this paper has been referenced 40,707 times on Google in the past 35 years. So it's been referenced more than 25,000 times just in our database alone. And this is the most famous reference to mediation and the way it was done for about 20 years until we got conditional process modeling. So if you want to see a lot of the hard mathematics behind it, here's where you need to go. I'm not going to go too far into it, but I will talk about a little bit of the math. But yeah, here's your reference if you want more about it. So with mediation, you have to test it through 3 regression models. That's it. You're running 3 regression. This is just a linear regression. This isn't anything special. This isn't a logistic. This isn't a Cox and Snell. This isn't anything difficult. These are just regular regression models, linear regressions that you're going to be running. And the steps are this: predict the outcome from the predictor. So does your independent variable predict your dependent variable? If so, move on to the next one. Predict the mediator from the predictor. Does your predictor predict your mediator? And if it does, move on to the next step. If not, stop. You do not have mediation. If at any time any of these steps say no, stop. You are not mediating. And then lastly, predict the outcome from both the predictor and the mediator at the same time. So you've got a simple linear regression here, a simple linear regression here, and a multiple regression here. Really easy analyses that you can do. It doesn't matter what stats package you're using. Just simple linear regression and multiple regression. So let's look at these conditions, because there's technically 4 conditions because step 3 has 2 parts to it. The predictor must significantly predict the outcome variable. You can see the relationship here. You have, this is what's known as your C path. I'm going to talk about your A path, your B path, your C path, and your C prime path. However, this is your C path, your independent variable to predict your dependent variable, X to predict Y, simple linear regression. I've got the formula down here. This is just a regression formula. Y equals mx plus b, or y equals the whatever x is times the slope plus your y-intercept, well, plus error. A lot of times they skip off the error. But does the independent variable cause or predict the dependent variable? If so, check it off. You've done step 1. Next step, this is your A path. Does the predictor predict the mediator? So just run another simple linear regression, your independent variable, X, predicting your mediator, M. Again, same thing, M equals your y-intercept plus your slope times X plus error, simple regression. We're not even worried about the dependent variable here. You notice there's no arrows going to it. So it's not even in the formula. It's not even in this regression equation. Just independent variable to predict your mediator. If it does not, stop. You do not have mediation, do not pass go, do not collect $200, you're done. You don't have mediation, write up this relationship. If this does predict it, move on to step 3. And here is the most complicated part of the whole process. Just put your independent variable and your mediator inside your linear regression to predict Y at the same time. This gets you your A path. Well, you've already got your A path, excuse me. Your A path came from step 2. This gets you, though, your B path and your C prime path. So your B path is just the relationship between M and Y, or your mediator and the dependent variable, your slope, for instance. Your C prime path is the relationship between your independent variable and your dependent variable. Now you may be asking, but wait, we did that in step 1. Why do we need it again? And why is it now C prime? Anytime you include another variable in a model, it's going to change the relationship. This relationship will change even slightly because you have included another thing to soak up variance. When you include another predictor, or if you include another condition, or if you include anything else in a model, these relationships change based on the amount of variance or the amount of error that's being soaked up by your new predictor. So it will change. It may be small, but it will change. Other times it'll be huge. As you'll see in the example I'm giving, it completely changes the effect. So in this case, the mediator must cause or predict the dependent variable controlling for the independent variable. So we already know this is significant. If this is significant, if your B path is significant, you basically have mediation. Now, the fourth step, which is arguably important, this is relatively controversial using the Barron and Kinney model. I follow it personally. If I do, well, I don't really use the Barron and Kinney model when I'm doing mediation that much. We'll talk about conditional process in a moment. But when before I run the conditional process, I always run a Barron and Kinney mediation just to see, because if it's not significant, conditional process is not going to be significant, and I'm going to try and save my time. But with the Barron and Kinney method, this relationship has to be weaker than this relationship. Your C prime path has to be weaker than your C path. And that's because your mediator has to be soaking up that difference. What the difference between this and this should be accounted for by this. And so where this is weaker than your C path is because of your mediator. And that's what you need for true old school traditional mediation. The predictor variable must predict the outcome variable less strongly in model 3 than in model 1. Your C prime must be weaker than your C relationship. So I just talked about the traditional steps to mediation. I run this all the time. Anytime I'm doing mediation, it's the first thing I'm going to do. I'm going to run the Barron and Kinney mediation because it's so fast. It runs so quickly. But you can't stop there. Sometimes you can still get away with it if you try to publish it, but more stat savvy journals, they're going to look at that and say, okay, that's cool. Now run the conditional process. Because there are criticisms in the Barron and Kinney steps, and it's just because we didn't have the technology at the time to do things the way we can do them now. So some of the criticisms, using simulated data, there were significant differences in the number of type 1 errors and power across steps. Barron and Kinney have low power for small effects. If you have small sample sizes, you're going to struggle with Barron and Kinney. On top of that, you're running a lot of tests. At minimum, you're running 3 analyses. You're running model 1 to get your C path, model 2 to get your A path, and model 3 to get your B path and your C prime path. That's inflating your type 1 error rate. The more tests you run, the more likely you've committed an error. That's definitely an issue. Other researchers have argued that the M to Y path may not be significant when X and M are highly correlated. This is a multicollinearity issue. So if X and M, so your independent variable and your mediator, if they are highly correlated, you have what's known as multicollinearity, which is a violation of the assumptions of your multiple regression. However, X and M have to be related for mediation to happen. So this is an issue that you can't really sidestep in Barron and Kinney. If they are highly correlated, that can impact your relationship between M and Y. So using these steps, there's just nothing you can really do about multicollinearity. So there's 2 other approaches, and I will give my recommendation for which one you should do. You can pretty much get away with any of them. I see both of them published, although I see bootstrapping published more. The 2 popular approaches for testing whether the C prime path is weaker than the C path, or whether mediations occurred, are what's known as the Sabel test and the bootstrapping model. The Sabel test was it's older than bootstrapping, because bootstrapping is absolutely a newer thing that we weren't able to do 20 years ago. Your Sabel test, basically, it's just going to test that relationship through. It's going to look at that relationship from X through M to Y. However, this test struggles on smaller sample sizes. And many times in medical research, we have small sample sizes. However, if you have 100 participants or more, run it if you want to. It does great at about 100 or more participants. So keep that in mind. The method I'm really going to be talking about, though, mostly is bootstrapping. And bootstrapping is fantastic because it doesn't matter how big your sample size is. You can get away with bootstrapping with 5 participants. I don't recommend it. There's other issues if you only have 5 participants. As far as a mediation goes, if you want to bootstrap 5 participants, go ahead. It'll handle it just fine. Now, I do have a little comment down there that their data shows there's about 90% agreement between all tests. That's why I often start with Barron and Kinney, because I know there's probably a 90% likelihood it's going to match my bootstrapping. So keep that in mind. Start with Barron and Kinney. It's time saver. It's really quick. If you don't have significance with Barron and Kinney, you might as well just assume you're not going to have it with bootstrapping or Sabel. But if you are significant, you do have mediation, now go on to the next step. Go on to the bootstrapping or the Sabel test. So let's first talk about what the Sabel test is. We're not going to spend a lot of time on this just because I don't think it's the proper way to do things. It's fine with 100 participants, but a lot of times we don't have it. So I'd rather spend more time talking about bootstrapping because we can do it with however many participants we want. So the Sabel test assesses the statistical significance of the indirect effect, or the A path and the B path together. In other words, it assesses whether a significant part of the relationship between X and Y is controlled by the mediator. Again, it looks at that A and that B path together. That's your indirect effect. So I have the formula down there. Your Sabel test is simply your A path times your B path divided by the square root of your A path squared times your standard error of your B path squared plus your B path squared times the standard error of your A path squared. That gets you your Sabel statistic. And depending on how large or small the Sabel statistic is, and depending on your degrees of freedom, you basically then go look it up in a table based on your AB equals 0, Z is greater than Z, 1 minus A. Again, looking at that very similar than the old school way of doing like a significance test. I don't recommend doing this. Some stats processors will give you a Sabel test. I think you can get it with Amos. That involves using structural equation modeling to do this, or to do mediation. I think you can also get it with M+. I know you can get it with R. You can get everything with R. I don't think SPSS gives you a Sabel test anymore. I think it used to, and I think it got rid of it because it integrated conditional process modeling. I don't know about SAS. If you are a SAS user, I don't know if it'll give you a Sabel test. So you may be stuck doing this the longhand way if you want a Sabel test. The issues with the Sabel test, other than the fact that it's highly dependent on your sample size, the distribution of AB is highly positively skewed. So that indirect effect is typically very skewed. And so thus relying on a method that assumes a normal distribution sampling distribution reduces the power. So again, all these are parametric tests. All this is just linear regression. It assumes normality. This is one thing that I've not mentioned that I'm hoping I'm able to get away with not mentioning at this point, is that you have to check your assumptions of your linear regression before you do this. Before you run any test, you need to be checking your assumptions. And if you violated your assumptions, it doesn't matter how good the test is, your data is wrong. You have to have correct assumptions. And so with the Sabel test, it's assuming a normal distribution because it's a linear regression. However, that distribution of your indirect effect is highly positively skewed, and that can cause problems, especially with smaller sample size. Now, once again, if you have a larger sample size, you can fall back on central limit theorem, and you can be pretty sure it's fine. You don't have to worry about too much. I know I put 100 there. That's what's published. For me personally, it's a personal feeling, so I can't back this up with science. I get wary if it's less than 200. If it's less than 200, that's when I start to get nervous, especially central limit theorem. But if you have 100 and want to run a Sabel test, theoretically and with the published data, you can get away with it. It's just a personal preference. I don't like to fall back on central limit theorem unless I have 200. So in other words, with this issue of the highly positive skew, the tail probability is going to be larger, again, a larger p-value, if we assume a normal distribution than if we assumed a skewed distribution. So all that to be said, I recommend bootstrapping. Bootstrapping, honestly, I recommend bootstrapping for everything. Bootstrapping fixes about every single problem that you can come up with. Bootstrap your t-test, bootstrap your correlation, bootstrap your regression, bootstrap everything. I recommend it highly. First off, you'll wow some reviewers. Half the reviewers won't even know what bootstrapping is. They'll just look at your results and say, okay, that's fine. On the other hand, bootstrapping is a really complex, or is a really powerful way to be more confident in your data. Ultimately, with bootstrapping, it allows you to resample your data in order to generate an empirical sampling distribution. So with bootstrapping, you're going to use your mean, your standard deviation, and your standard error of whatever you found, and it's going to create test data. It's going to synthesize data for you, and it's going to use that mean, that standard deviation, that standard error to create those distributions of data. And by doing that, it's then going to resample all of this and test your data again, however many times as you want. Typically, on average, if you're bootstrapping 5,000 times. And that's why this method wasn't invented until recently. We just didn't have the processing power to do this. It takes a couple seconds. If you bootstrap 5,000 times, your analysis is probably going to be running for about 15 seconds. You can bootstrap up to 100,000 times, probably 1,000,000 times. Again, every time you bootstrap longer, it's going to take longer to run, but it's going to be a stronger analysis because you have your original data, then you found the effect there, but also you now have confidence intervals around it based on this bootstrapping on data that has been created using the constraints that you set up with your data. And those constraints allow you to get more and more samples and just be more confident because it's going to generate normal distributions based on what you found. It's going to look at your mean and it's going to look at your standard deviation and create a standard or a normal distribution of data points within that normal distribution and just keep running the same regression over and or the same t-test or the same correlation or the same ANOVA over and over and over again until you get to the number of bootstraps that you have specified, typically 5,000. It's really powerful and you can do it on everything and I highly recommend it. But for mediation, you kind of have to have it unless you're going to do a Sabel test. And so using this resampled data or this synthetic data, researchers can then use the bootstrap estimate of your indirect effect, AB, along with the standard error of the bootstrap estimates to compute a z-statistic or a confidence interval. When you have 5,000 resamples, it doesn't matter how skewed your data is. 5,000 is going to fall back on central limit theorem, and you're going to be able to say this is a normal distribution. You don't have to worry about it anymore. Anytime you have non-normal data, if you have if your data is non-normal, bootstrap it. Easy way around it without having to worry about doing non-parametric tests because non-parametric tests have issues of their own. They have assumptions that you have to meet that if you violate them, there are problems there. Bootstrapping, the only assumption is you have enough data to get statistics. You have enough data to get a mean and a standard deviation. If you can get that, you can bootstrap your data. Now, bootstrapping doesn't fix sloppy data, it doesn't fix bad science, it doesn't fix poor research methods. Statistically, though, bootstrapping should become your best friend and is a way to get really strong data that you can be very confident in with not a large sample or with issues in your distribution or issues where you violated assumption. You don't have to worry about a normal distribution. You don't have to worry about skewed with 5,000 participants. You have central limit theorem to back yourself up. So before we go into this example, I probably should have done this a little bit earlier, but I have an example here that we're going to look at, and we're going to run a mediation, a Barron and Kinney mediation. The reason I'm not going to bootstrap it is because, unfortunately, Cook SPSS at the moment does not allow us to download process. Process is an SPSS macro. It is an R macro, and it is a SAS macro. You can use it on all three that allows you to do moderation, mediation, moderated mediation. It allows you to bootstrap really simply. It's to the point SPSS is about to integrate it, but there's some issues legality because it was created as a third-party thing. So they want to integrate it, but it's not there yet. So you have to download the process macro. It's super safe if you have SPSS at home. I recommend it. I have it on all my personal laptops that have SPSS. I've used it for years. Pretty much everyone who's doing hardcore statistics have process on their computers. There's books written about it. It's fantastic. Unfortunately, because of security issues, we're trying to get it through right now. We're working on it. We can't get process, unfortunately. But we are trying. So I'm only going to talk about the Barron and Kinney steps. I'm only going to show you a Barron and Kinney example. And then in the PowerPoint, I have the process steps. So if you get process on your own, if you get if it eventually gets passed here at Cook where you can get process, you'll know how to do it. Because all process does, it just gives you another thing under regression. So it's just down here under probit, it just says process. And it's just a new way to click on it. But let's look at our data here. We have an independent variable, a mediator, and a dependent variable. If you remember, that's all you have to have for mediation, or at least test mediation. This data is completely synthetic. I created this data. Yes, it was incredibly difficult to make, but this is the first time I've ever been successful at creating a mediated relationship. So I was actually quite proud of myself for being able to do that. But this is just fake data that I just made up for purposes of teaching. So step one, first thing we want to do is we want to see the CPAth. Does the IV or your predictor have a relationship with your dependent variable or your outcome variable? So we're just going to go to regression. Again, whatever stats package you use, this is just a simple linear regression. I'm going to put my IV in the dependent or in the independent box and my DV in the dependent box. I'm going to request part and partial correlations because this gives us our estimate of effect size. I also like confidence intervals. I typically, you have to publish anymore, you have to have confidence intervals, so just request them. And then I'm going to run it. So scroll on down and let's look at the relationship between our IV and our DV. As you can see, it is significant. It is a positive relationship. So as our IV goes up, our DV also goes up. We have a significant relationship. Those confidence intervals do not include 0. And we can square our part correlation here to get our measure of effect size. So I'm just going to take my calculator and I'm going to square that. 0.616. So our measure of effect size, or R square, is 0.379 or 0.38. That's a big relationship. It's predicting about 38% of the variance. So we have a relationship there. That is step one of this model done. We have our CPath. Now, let's go to step 2 and look at our APath. I'm going to pull the dependent variable out, and I'm going to put the mediator as the dependent variable this time to let the IV predict the mediator. I'm going to click OK. I'm going to scroll on down. We can see a positive, a quite strong positive relationship. It is significant. So as the IV goes up, your mediator also goes up. Confidence intervals do not include 0. And for our measure of effect size, it's going to be a really big effect. 0.788 squared. We have about 0.62. So the independent variable is predicting 62% of the variance or the change in the mediator. So check. That is our APath, and step 2 is complete. Now let's run the last step. I'm just going to run another regression. This time, though, it's a multiple regression. I'm going to put our independent variable and our mediator in the independent fields box. And I'm going to put our dependent variable as our predicted value, as our outcome variable. Again, do this whatever stats package you want. This is all it takes. Just 2 simple linear regressions and a multiple regression. So I'm going to go down. Okay. First thing we're going to look at our mediator. We have a positive relationship. It is significant. So as the mediator goes up, the dependent variable also goes up. confidence intervals do not include 0. And as far as our effect size go, I'm just going to square that partial correlation. So 0.31. So it's predicting about 30% or 31% of the variance in the dependent variable. However, let's look at our independent variable now. This has changed. This is negative now. If you remember, it was a positive relationship when it was run by itself. Again, this is our C prime path. However, it is no longer significant. So our mediator is able to explain all of the relationship between our independent variable and our dependent variable. This is what's known as full mediation, because our IV is no longer significant. Our C prime path is not significant. Now, if our C prime path stayed significant, that's what's known as partial mediation, that it explains some of the relationship, but not all of it. Maybe there's another mediator in there. We can toss more and more mediators as needed. But for this case, this is full mediation. This IV does not explain any of the difference or the change in the dependent variable when accounting for the mediator. However, we know that the independent variable, from that first regression, we know that the independent variable is related to the dependent variable. So this shows us that the independent variable is only related to the dependent variable through the mediator. And your mediator is just going to come from theory. You're going to want to predict something based on theory, based on practice, that should explain this relationship. And it's always really fun, in my opinion, when you're doing a mediation analysis and you get this full mediation down here to where your IV is no longer significant. I always think that's such a cool result, because you completely flip this finding that was highly significant and is no longer significant. But that's it. Based on the Barron and Kinney steps, you have mediation. Now, you can now choose to run a Sabel test using this is your C prime path. Here's your B path, so you have that. Here's your standard error for your B path. And here is your A path. Here's your standard error for your A path. All you have to do is plug those into that formula that I showed you, and you can do a Sabel test. Now, the big issue here is we only have 15 samples, so that Sabel test will be highly, highly likely to be incorrect. But again, we can bootstrap this and have no problems with it. So let's go back to this, because I want to talk about conditional process modeling. Because conditional process and the process way to do mediation, that's honestly the most correct way to do it, in my opinion, the safest way to do it. And I'm going to talk you through an example here and talk you through how you would do the steps in process. So the example I have is tablets like the iPad are very popular. A company owner was interested in how to make his brand of tablets more desirable. He collected data on how cool people perceived a product's advertising to be, so how cool they think, how cool they thought the product was, and how desirable they found the product. Let's see if advertising and product desirability is mediated by how cool people think the product is. So we want to see, does advertising predict product desirability through how cool they think the product is? Or in other words, does the advertising change how people think the product is cool, and does that change how desirable it is? So we have, I should also mention there is another stats package you can use. It's called Indirect. It's also by Preacher and Hayes. Andy Hayes is sort of the go-to statistician anymore. He's the one who created this Indirect, this macro called Indirect. He also created Process. This is what it looks like if you have those two downloaded, if you have that macro for Indirect, if you have that macro for Process. This is just your regression. Analyze regression, and there they are. In this case, we're going to use Process, though. So when you click on Process, this is what comes up. It does every bit of this by itself. You have all your variables here. You're going to move your independent variable, or cool, here. You're going to how cool the advertising, excuse me. You're going to move your mediator here where it says proposed mediator. And you're going to move your dependent variable here of product desirability. How many resamples do you want? How many bootstraps? So in this case, I just used the thousands. You can get away with 1,000. Some journals may question it. You can change your confidence interval if you want. I don't recommend it. But ultimately, this is saying we're going to rerun this relationship 1,000 times and make sure it does in fact work. And this is the outcome you're going to get in SPSS or R or in SAS, because you can get this macro for all of it. So you can see here, we have our A path. It even labels everything for you. So your IV to your mediator. We have, this is basically our slope. This is our predictability and our significance value. It is significant. Here's our direct effect of the mediator onto the dependent variable, or our B path. We do see our mediator does in fact predict our, it does in fact predict our dependent variable. Here is our C path. So this is just, does our independent variable or does advertising predict desirability by itself? And you can see here it does. I've got that C path written out here. Now, though, we have that C prime path. And as you can see, by the inclusion of the mediator, the C prime path is weaker than your C path. You can see, again, A path, B path, I've got them color coordinated, and C prime path. This would suggest we have mediation. We have an effect of advertising through how cool they view the product to predict desirability. So good advertising makes people think a product is cooler, which makes people want it more. That's what this is showing. On the other hand, just by itself, it's saying good advertising makes people want it more. That's what we see here, but that's not the full picture. Something else is affecting it. And in this case, it is the coolness of the product. And you can put any mediator you want in here so long as it's theoretically supported. Ultimately, you need to go back to the data. You need to go back to the literature to look and see what variables you want to include as mediator. Down here, we have our bootstrap results for the indirect effect, and we get confidence intervals down here. And we have our actual effects. So right here's our confidence intervals. As you can see, 0 is not included in this. This is the confidence interval of this path right here, this indirect effect. This is the last step to mediation that Barron and Kenny do not do. They do not test the significance of these, the A and the B path together, the full indirect effect. And that's what your bootstrapping or your Sabel test does. In this case, the confidence interval does not include 0. So we can be confident that this is mediation. These are the rest of your statistics to go with it. So this is your this is ultimately your coefficient, and here's your standard error of your coefficient for your indirect effect. Some journals care about it, others don't. It just depends, but here it is if you need it. This is the thing that matters, is your confidence intervals. So I told you wrong that what we just did it with was using indirect. I'm very sorry for that. Process is the same method. It even looks very similar. You just have a couple more boxes that you can completely ignore. So again, the independent variable, I put the advertisement. In the M variable, or my mediator, I put the product cool, outcome desirability. Process has multiple models. If you want to know what each model is, you can find them online. You can just Google what's process models, and there's a handbook with it. Process model 4 is mediation. So if you're doing simple mediation, just model 4. Your number of bootstraps, your confidence intervals. You don't have to worry about changing anything else. Now, I do often click the the options, because I like getting the Sabel test just to have it. This will give you your Sabel test. This is already checked. That's all you need. If you want to center it, you can. If you want heteroscedasticities, consistent SEs, you can. If you want data for plotting, if you're doing a different model, you can. If you want effect sizes, I don't know why I didn't check that this time. I'm sorry for that, because I almost always check effect sizes because you need a measure of effect size. But yeah, it's just more options. That's all it gives you. The outcome looks the same. Here's your A path, your mediator. Here is your B path, your mediator to predict your dependent variable. It's a little bit less user-friendly, I would say, because it's doing more than just mediation. So you remember in indirect, it said, here's your A path, here's your B path, here's your C prime. In this case, it doesn't. You just have to know what these things are. You have to look and say, okay, so advertisement coolness is predicting product. Or product coolness. So in other words, this would be your A path. And here you'd have to look, okay, product and advertisement are predicting desirability. Oh, this must be my B path and my C prime path. And down here in your direct effect, which is your, which is again your C prime path. So same results, nothing's going to change. You got your p-values, you got your coefficient variables, and you've got your confidence intervals for everything. But down here, we have what we care about. Here's our Sabel test. It gives us our Z value for our Sabel test and a p-value for our Sabel test. So it's actually 0.0157. I just rounded it to 0.02. So if you want an easy Sabel test, there you go. So I have several write-up examples here. For the sake of time, we're not really going to go through them too much. These are studies that either my old lab did or I did. And I've just got some examples that were published and how we've written up mediation. So the big thing down here is this mediation of well-being by nostalgia. To examine whether nostalgia mediated the effects of website on well-being, we followed conventional guidelines for assessing mediation. Of course, and Kenny, add to that 40,000 citations strong. Meeting the first criterion, there was indeed a significant relationship between the predictor variable and the dependent variable. The second step examined the relationship between the predictor variable and the mediator. As noted, this relationship was observed. Third analyses examined the relationship between the mediator and dependent variables while controlling for the predictor variable. There was a significant relationship between nostalgia and well-being when controlling for website conditions. Positive affect, here's all of our stats. Life satisfaction, here's all of our stats. And the final step examined the relationship between the predictor variable and the dependent variable when the mediator was in the model. When nostalgia scores were entered in the model as a covariate, the effect of website on positive affect and stats became non-significant. This is again our C prime path. However, the effect of website on life satisfaction remains significant, suggesting partial mediation. This is also a C prime path. This is technically serial mediation. Although there are clear trends in the pattern of results, Sabel tests indicated that there were in fact significant attenuations. Positive affect and life satisfaction, these are indirect effects. So sometimes you can use attenuation. That's technically another term for mediation. I did go on to talk about the Preacher and Hayes bootstrapping down here, using that model, examined whether thoughts of nostalgia mediated the relationship. Positive affect and life satisfaction were regressed onto website condition with thoughts of nostalgia entered as the mediator. 5,000 bootstrap resamples were performed and 95% confidence intervals obtained for the indirect effect did not contain zero. These are our confidence intervals. In reality, anymore, you can just get away with this. You can just say this and you're fine. Now, give these statistics, give them probably in a table. This is all you really need to say anymore. This is an older paper that whenever process was still starting to get used, starting to get used in the field. You can just get away with this though anymore and just include a table for the other stats because this is all that really matters. If you have these significant confidence intervals, you're set, you're done, you have mediation. Here's the figure that I included in the paper. So you can see, here's our A path, here's our B path, here's our C path and our C prime path. Total effects is C path, direct effect is C prime. That's all you need. Sometimes you may want to include the standard error there. You may want to include more statistics. It just depends on what the journal wants. Here's how it's described: the indirect effect of the website on positive affect and life satisfaction through nostalgia. Mediational results of the effect of nostalgia on the relationship between website and relationship need satisfaction in all path models. Star indicates significance at whatever level you want to set it at. That's it. You need that one paragraph and you need these tables. You don't need anything else to publish mediation anymore. So I know we just went through a lot, but that is mediation. There's not really anything more to it. You can get really complex and start doing moderated mediation, where you start to look at does the mediator interact with something else, or does it interact with a moderator, or does your independent variable and a moderator combine together to predict a mediator, which further predicts a dependent variable? You do those the exact same way. You would still get your A path of your moderator and your independent variable to predict your mediator. If your interaction predicts your mediator and your mediator predicts your dependent variable, you have mediated moderation. Similarly, if you want to do moderated mediation where your mediator has a moderator, all you have to do is get your A path, then do an interaction term between your mediator and your moderator. And if your A path, or if your independent variable predicts your interaction terms and your interaction terms go on to predict your dependent variable, you now have moderated mediation. You can also just use process to do all of it for you without having to create the difficult all the interaction terms. And all you'd have to do is look up which process model does moderated mediation, which process model does mediated moderation, and just follow the instructions there. But that's it for mediation. It's literally 2 simple linear regressions and a multiple regression, as well as a little bit more complex stuff with bootstrapping. But all you have to do is click a box and say, yes, please bootstrap this for me, and you're done. Are there any questions?